Hey class, this is Mr. Roberts at Shasta High School, and let's face it, it's Friday afternoon, April 1st, and that test we just took was pretty tough. So I'm going to go ahead and go through the solutions for this, and at this point you should have your original copy of your test in your possession, and I want you to go through and carefully correct any items that you may have missed by watching and listening to this presentation. First of all, doing a problem is not really indicative of understanding the problem. So as you watch these, just realize that you just have one level of understanding. You know that it's possible to find, in case of number one, the x and y values that make this true. That doesn't mean you have the solution. So let's go ahead and begin with question one. So in question one, we're asked to find solutions to two different systems of equations using any technique we want. This first one, I don't know, looking at it, there's probably a lot of different things I can do. If I wanted to use elimination, I'd probably rewrite it and get it set up so maybe I could manipulate so that my 2y would cancel with 2y. But honestly, I just now saw this. I did not see it when I wrote my original answer key, but just looking at it right now, it occurs to me that, hey, this is equivalent to 2y, right? It says 2y is 3x minus 4. What's amazing about that, and I literally just saw this now, is that the top equation needs 2y. So this is probably, I thought this was going to be difficult, but this is probably the most straightforward substitution I've seen. I can write this as 4x plus 2y. 2y is the same thing as 3x minus 4, and that equals 10. Therefore, 7x minus 4 is 10. 7x is 14. And of course, we know therefore that x is the number 2. So just like that, I was able to figure out what x is. X is 2. Now that we know that the value of x is 2, we're going to take that and plug it back into either one of the original two equations to figure out what y is. I guess I'm just going to use the top one. So this says 4 times x, right? Remember, x is 2. So 4 times x would be 8 plus 2y is 10. If I subtract 8 from both sides, I get that 2y is 2. And then if I divide both sides by 2, I get y is 1. Now, that's not the only way you could do this. There's lots of other ways you can do this, but it is kind of nice to pause and just verify that this actually works. So I think my solution is 2, 1. And again, if I just check real quick, here, this is 2. So 2 times 4 would give me 8 plus 2. That is 10. So it checks in the top equation. In the bottom equation, right, y is the number 2, or y is the number 1 rather. So 2 times 1 would be 2 is 3 times 2 is 6, and 6 minus 4 is 2. So that checks also. So that is definitely the solution to number 1a. It's 2, 1. Let's look at b. We may not find anything quite as nice as we did with part A, but looking at this, I guess this top equation, I'm just going to go ahead and use fraction busters and get rid of the 3. So I'm going to rewrite this, and I don't know that this is particularly helpful, but I'm going to rewrite this as, and here what I'm doing is I'm multiplying every single term by 3. This is going to give me 2x plus 6y is the number 30. I don't know if that helped me. In the bottom equation, this is y minus 3 equals, I'll go ahead and distribute the 1/2. This is going to be 1/2 x, and then that would be a minus 3, right? Because 1/2, 1/2 times x is 1/2 x, 1/2 times negative 6 would be negative 3. And I noticed, because this is an opportunity, because both of them have a negative 3 exactly, I could add 3 to both sides. And if I add a 3 on each side, this is going to become y is the same thing as 1/2 x. So it turns out that is a great substitution value, right? I can take this, right, y is equal to 1/2 x, and I can sub that into this equation that I have here. So doing that, probably took up too much room with that blue line. Let's go this way. I'm going to put it in right there. So doing that, right, this equation is going to become 2 times x, right, 2x plus 6 times 1/2 x, and that will be 30. Well, 6 times 1/2 x is 3x, so I'm looking at 2x plus 3x is 30. 5x is 30, therefore x is the number 6. And if I take that value of x and I plug it into the fact that y is equal to 1/2 x, right? If x is 6, I could plug that in here. This is y is the number 3. 1/2 times 6 is 3. So I think this one's solution is 6, 3. And I'll write that there, and I'm relatively happy with it, but you know that I like to kind of double check. So kind of just cleaning up and looking at the original 2 problems, or 2 equations, this original system. In the top one, if x is 6, 2/3 of x would become, let's see, 6 divided would be 4. 4 plus, and then 2 times 3, because y is 3, 2 times 3 would be 6. Yeah, that's definitely 10. So the checks in the top equation. For the bottom equation, ooh, that's interesting. So y is 3, so 3 minus 3 gives me 0 on the left-hand side. And over on the right-hand side, when I plug 6 in for x, I get 6 minus 6, which is 0. And 0 times 1/2 is 0. So this ends up becoming 0 is 0. So absolutely, this is the point, 6, 3, in which both of these lines would meet up with each other. The Shasta High School track team is selling boxes of candy as a fundraiser. Taylor ordered 4 small boxes and 1 large box, and that cost her $28. Chris ordered 3 small boxes and 2 large boxes for $31. What is the price for each size box? So this problem is just an excuse for practicing linear systems. So I'm going to create a let statement here. I'm going to say let, I'm going to go with small and large. So small and large. So S is going to be the cost, not how many, but the cost of a small box of ants, no candy. And L is going to be the cost of a large box of candy. And I know from this information presented, and this is how I'm going to write my system, is if I have, let's see, what does it say? It says Taylor ordered 4 small boxes, so 4 of the small boxes plus 1 large box, so just 1 L, and that cost her $28. And Chris, is it Chris? Yeah. Ordered 3 of the small boxes plus 2 of the large boxes. Yep, 2 of the large boxes, and that cost him $31. So any method we have for solving this system would be great. I feel like doing substitution. So I'm going to take this top equation and I'm going to write it so that L is alone. So if I subtract 4s from both sides, I get that L is 28 minus 4s. You could have definitely set this up for substitution, or for elimination. I'm just using substitution. Now that I have that, this is a valid substitution for L, and my intent is to replace L in the second equation with that valid substitution. So this second equation is going to become, after the substitution, 3s plus 2 times the quantity of 28 minus 4s. Got to be careful because that s can start to look like a 5 if I'm not careful. In fact, this is not 35, this is 3s, right? So 3s plus 2 times 28 minus 4s is equal to 31. Using the distributive property, 2 times 28 is, I believe, 56. So I've got 3s plus 56 minus 8s is 31. If I combine my terms with s, right, I've got 3s and minus 8s. That's going to become 56 minus 5s is 31. And I think I'm going to go ahead and add 5s to both sides. So 56 equals 31 plus 5s. And if I subtract 31 from each side, we got 56 minus 31. Ooh, are you really doing that? Yeah, 6 minus 1 is 5. And that's 25 is 5s. Therefore, when I divide both sides by 5, it looks like I'm getting 5 is the value of s. So I think the small box of candy cost $5. Right? Because that's what I got for s, and that was the variable that defined the cost of the small boxes. And then for the large boxes, I do have this equation that was derived from the first equation, right, by subtracting 4s from each side. So I can just use this, and I'm just going to plug this value 5 into this equation. So it says the large boxes should be $28, right? L should equal 28 minus 4 times 5, which looks like 28 minus 20, which looks like $8. So the large boxes cost $8. Oops. All right. A couple things, good recommendations, right, is plug those in. 4 times s plus 8 is 28, right? 4 times 5 plus 8 is 28. 3 times s is $15, plus 2 times 8 is 16, and yet 15 plus 16 is 31. So they definitely check. Onto our second page. It says plot T, R, and U to form a triangle. So let's go ahead and plot those points. T lives at -6, -1. So here's point T. And then point R lives at 2, 3. So this is my point R. Probably should label these. There's R. There's T. And my last point is point U. And point U is at 3, -4. And it says connect them to form a triangle. So there they are connected. Next it says determine the midpoint of TR algebraically and label the point P on the grid. So, okay, so by algebraically, I guess I'm not exactly sure, but I think this is what I meant. If I look at these, those are my x values, and these are my y values for these points. And I know that the location of the midpoint is the average of the x's and the average of the y's. So if I looked at this, the midpoint should be at -6 plus 1. And I'm going to take half of that. So -6 plus 2, which would be -4 divided by 2, which should be -2. So I believe -2 is going to be the x coordinate for my midpoint. And then for the y's, I've got a -1 plus a 3, and I'm going to take half of that. So that ends up being 2/2, which is 1. So my midpoint, I believe, is the point where x is -2 and y is 1. So that looks pretty convincing. And also I can kind of confirm this in terms of the slope, because I can see here there's a rise of 2 and a run of 4, a rise of 2 and a run of 4. So I believe we've got the midpoint. And it also says to label that midpoint P. So this was a missed part of the test for some of us. So I'm going to label that point P. Next question, it says find the distance between points P and U. write your answer in simplified radical form. So if I'm thinking about that, right, the distance from P to U, I can sketch it, right? It's like this is what I'm trying to find. Well, how would I find that distance? Well, I would consider the right triangle that would bound that diagonal, right? So I can look at this particular rise, and I could look at this run. And if I look at those, I think they're each 5 units, right? This is 1, 2, 3, 4, 5. Yeah, this is 5 units. And this is 1, 2, 3, 4, 5 units. That's 5 units also. So what we're looking at here for this distance between these is the, what is it, the square root of 5 squared plus 5 squared, which looks like the square root of 50. And that's 50 is 2 times 25, so this is the same thing as the square root of 25 times 2. So simplified radical version would be 5 root 2. 5 root 2. And in fact, if we look at our calculator, we can say we want the square root of 5 squared plus 5 squared. And it gives us, 5 root 2. And if we want it as a decimal approximation, it would be 7.07. I think it says round to the nearest tenth. So the two things we could have written down for our answers for the distance here was we could have written down 5 times the square root of 2, which is about 7.1 units, right? They're both just linear units when rounding to the nearest whole number. All right, and the last thing here, it says find the area of triangle true. This is not trivial. It's not ridiculously hard, but it's a bit of a challenge. So if we're going to find the area of this triangle, I think a good strategy is to think about a rectangle that bounds the entire thing, and then we're going to subtract some triangles from it. It's easy to find the triangles, the area of a triangle on the Cartesian coordinate plane when you know that your legs are perpendicular to each other, right? When they're meeting at right angles. So it's really easy for me to say, well, let's consider this whole rectangle. Now, my area is not this whole rectangle. And it turns out my area is not half of this rectangle either, right? The area of the triangle that I'm trying to find, which lives in here, right? This is the area of what we're trying to find. This triangle, its area is going to be the area of the rectangle minus a few things, right? We need to subtract this region, right? We're going to subtract this, we're going to subtract this, and we're going to subtract this. And it looks tough, but finding the areas of those triangles is not bad because, for example, this is 4 tall, and this is 1, 2, 3, 4, 5, 6, 7, 8. 8 long. 4 times 8. Is that really 4 times 8? 2, 6, 4, 1, 2, 3, 4 times 8. So 4 times 8 is 32. 16 and 16, and then half of that. 32, half of that, 16. So this should be an area of 16. That's something I'm going to be taking away from the area of this big purple rectangle. Something else I need to take away is this triangle that's 3 by, what is this? 1, 2, 3, 4, 5, 6, 7, 8, 9. 3 by 9. So 3 times 9 divided by 2 is 27 halves, which is some fraction. I'm not good at that. 27, well, yeah, I am. It's like 26. It's 13 and a half. It's 13.5. And then the other part that I have here is this one that is 1 by 1, 2, 3, 4, 5, 6, 7. So it's 1 by 7. 1 times 7 is 7, and half of that would be 3.5. So I'll circle these things. The 13.5, the 16, and the 3.5 are all things that we're going to subtract. But you say subtract from what? Well, this rectangle, the purple rectangle, right, the original one that I drew here. Can I make this pen wider to make this more dramatic? This rectangle one of the dimensions of it is 7, right? I know it's 7 tall. And across, what is it? I can't even see it. It's going from 6 to 3. It's 9. So this rectangle is 6 times 9. Is it 6 times 6 times 9? That's not 6 times 9. But no, this is 7. This is 7. 1, 2, 3, 4, 5, 6, 7. Yeah, from -4 to 3 is 7. So one of the dimensions is 7. That's a terrible pen. Let me go to this one. It's 7. And the other one is from -6 to +3 is 9. So we've got the dimensions of 6 by 9. So the area of that whole rectangle is 42 units. So what I'm going to do is I'm going to take the 42 units, which is the whole thing. Is that? Oh, I'm not doing too well. It's not 6 times 7. This is a 9, and I think I said it right. So I need 9 times 7. This whole rectangle has an area of 63. I apologize for that. Thank you for those of you that were screaming at your camera, your phones. I could hear you, and it corrected me, although that happens in the future. So this is 63, and I need to take away from that 16. And I also need to subtract from that 13.5. And I also need to subtract from that 3.5. So I'm not going to lie. It's Friday afternoon. I'm tired. Let me get a calculator. So I'm going to go 63 minus, I've got a keyboard here, minus 16 minus 13.5 and then minus 3.5. And I get 30. So, so this, I guess that must add up to 13 then. So I'm going to have 63 minus 63 minus 33. Yeah, this must be 33. So 63 minus 33 is 30 units squared. Now, it is Friday afternoon and I am tired, so let me double check this. So if I add those numbers up, 16 plus 13.5 plus 3.5, I do get 33. And yes, 63 minus 33 is indeed 30. So the area of that is 30. Next, we have two tables here. One we're told is arithmetic. The other one we are told is geometric, and we're supposed to find the missing values of the table, but then write functions. One of them says, and I'll just read it, says, write an equation in the form y equals mx plus b that fits this table. That's clever. It's arithmetic, right? It's arithmetic, and I'm given the fact that, hey, arithmetic sequences are linear, so it's going to be a line that I need to fit. And if you look at this, I've got the number 1 and I'm adding something. I'm adding it again, and I'm adding it a third time, and I'm growing from 1 to 8. What am I adding? Well, one way of thinking that is, well, what's the slope of this line, right? What's the line growing by? The slope is my change in y, so I can look at change in y, which would be 8 minus 1 over the change in my x's. I did 8 minus 1, so I'll do 4 minus 1. It looks like I've got 7 thirds. So I'm adding 7 thirds. Oops. I'm adding 7 thirds each time. So 1/3. Actually, let me put that on a calculator. I'm so excited. Let me just verify that. No, not that. Not me. The calculator. There we go. So if I take the number 1 and I add, 1. I'm sorry. Take the number 1 and I add. Actually, let me do this 1, and I'll say add 7 thirds. Right? When I do that, it goes from 7 thirds to 10 thirds to 17 thirds to 8. Oh, let me write these down. That's cool. So this was 10 thirds. This was 17 thirds to 8, and then the next one is 31 thirds. 31 thirds. And if I want to go backwards, because I need to figure out my 0th time, I could say that's fun. I'm happy that I got that, but let me do this now. let me take my answer and I'm going to subtract 7/3. So now, no, not 7. Well, that is, right, minus, I'm going to enter it as a fraction, 7/3. So when I do that once, you can see I'm back at 8. Then I'm at 17/3, and then 10/3, and then 1. And my 0th term is -4/3, which is great because now I can just write down what my 0th term is without doing what we normally do to solve for b or y-intercept. I know what it is. So this equation is y is equal to, I'm adding 7/3 each time, right? Multiplication shows that repeated addition of 7/3. And my 0th term is -4/3. All right, so that's A. If I look at B, I'm told that this sequence is geometric. One thing that I know is geometric sequences involve repeated multiplication. So I've got this number 5103. I'm going to multiply by some value b, and again, and again, and again, and it's going to transform 1503 into 63. In other words, 5103 times b, 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 b by a bunch of b's is going to become the number 63. Right? 5103 bb, bb is 63. Well, we can do better. 5103 times b to the 4th power is 63. Therefore, b to the 4th power is, let me write that as a fraction. Let's see, 63 over 5103, right? I'm dividing both sides. So it's going to be 63 over 5103. Fun fact, ooh, really? That does reduce. So b to the 4th power is 1 over 81. Now, we've talked about this. If I want to undo raising something to the 4th power, I can decide to raise each side of this to the 1/4 power. So I'm going to raise this to the 1/4 power and this side to the 1/4 power. Certainly, if you have equal things and you raise both sides to that identical power 1/4, you're going to get equal things. Over on that left-hand side, when I look at it, hey, that's nice. I've got 4 to the 1/4. Beautiful. That's why I picked 1/4, because this makes this b to the 1st, or just b. On the other side, if I take that 1 over 81 and I raise that to the 1/4 power, it tells me, hey, b is 1/3. So I can see here that I'm multiplying by 1/3 each time. And in fact, I can take the 5103, I'll enter that, and I'm going to say times 1/3. And if I do that, that will now give me the, oh good, I got this term now. This is 1701. Press enter again, it gives me 567. Enter again, it gives me 189. That's great. If I want to go the other direction, instead of multiplying by 1/3, I can divide by 1/3, or I can just multiply by 3. But I'm going to show this is, I'm going to say let's divide by 1/3. So notice what happens when I do this. It goes back to the, so it goes from that 189 back to 567, back to 1701, back to 5103. My first term has to be 15,309, and my very first term would have to be 45,927. There we go. That's it. So if I look at this now, this is fabulous, right? I know in an exponential sequence that, well, one of the ways of writing it is using the 0th term. This ends up being a. So I can say that this is y equals a 45,927 times b 1/3 raised to the x power. And another thing that we have at our disposal, right, is anytime I want, I could say, hey, let's look at that as a table real quickly. Let me clear you. So I'll say 4, 5, 9, 2, 7 times, I'm going to grab this fraction 1/3. Oops, I always do that wrong. Let me delete that, get out of there, close it, and then raise that to the x power. So what's nice is I'm going to go with auto. I'm going to make it start at 0 and step by 1. So and then OK. So you can see this generates the exact same table we can see that we've written down here, right? So we can see we've got the 0 term, the first term, the second term, the third term, the fourth term, the fifth term, the sixth. Yeah. They're all here. They're all here. We got them. All right, so pretty confident in that problem as well, because it definitely produced the two known values, right? When I gave it 2, it gave me 5103, and when I gave it 6, it gave me 63. So let's move on to fourth page and ask the calculator to go away. Thank you. So this says simplify each expression completely. Common factors or negative exponents are not allowed. So one of the things we talked about recently was that if you have a fraction raised to a negative power, right, we observe this on our calculator. In fact, I could throw the calculator back up here and show you this observation. If we have something like if I take 2/3, yeah, I'll do that, 2/3, and I raise that to the power of, I'll just do -1. When I raise a fraction to a negative power, notice what happens, right? All of a sudden this became, instead of 2/3, it became the reciprocal of it. It became 3/2. If I was raising this instead of to the negative first to the negative second, watch what it does. So you can see it does do the reciprocal, so it becomes 3/2, but then it squares that, so it becomes 9/3. So by observations, right, we can infer that this is nice. We can get rid of this negative exponent by just rewriting this as, this is going to be equivalent to 3x over 2x squared to the positive third power, right? We're going to cube that. Now, before I cube it, I just noticed that there is a common factor of x inside of the parentheses. So I can definitely do this substitution. I'm going to replace the thing inside the parentheses with just 3 over 2x, because I think it's almost clear that x over x squared is just 1 over x. So clean that up a little bit, and now I just need to cube this thing, which means multiply it by itself. So if I'm uncomfortable or unsure, I might write it out. 3 over 2x times 3 over 2x times 3 over 2x. In my numerator, I've got 3 times 3 times 3, which is 27. And in the denominator, I have 2x, 2x, 2x. 2 times 2 times 2 is 8. And I have 3 factors of x, so 28 over 8x cubed. For b, let's see here. Couple things. So I do have this a to the negative third, and one of my favorite tools from the beginning of the year is to go ahead and use the giant 1 to take care of this negative exponent. So if I multiply the denominator by a to the third, and I would have to multiply the numerator by a to the third also, right? The thinking here is I have a thing, and if you multiply a thing by the number 1, you don't change it. So in this case, I've just introduced a new factor of 1. What's nice about it is a to the negative third times a to the positive third is a to the 0, which equals just the number 1. The bottom line is that my denominator now just has b to the third in it, and my numerator has 5 factors of a, right? aa times aaa. So this is a to the 5th. Oops, and it has b squared also. Last thing I can see is, yes, I've got b squared over bbb, right? I can say bb over bbb. definitely there's a giant one of b squared, right? So that's gone, and I'm left with a single factor of b in my denominator. So this final answer will be a to the 5th power divided by b. For C, oh, I just lost everything. Sorry about that. Didn't want to make you seasick. Here we go. Haha, C, sick. For C, let's see. I think I'm going to process this first. So I've got 2a to the 4th. That's a 2a, 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 2a. 2 to the 4th is 2 times 2 is 4, times 2 is 8, it's 16. So this is 16a to the 4th power. Another thing I can do is there's a factor of a and then a to the negative 2nd. So together those make a to the negative 1st. And there is a grouping of 3 factors of b cubed. Almost done. I can definitely take the a to the 1st and a to the 4th. I'm sorry, a to the negative 1st times a to the 4th, and that's going to give me a cubed. So when I look at this, there is 16 is one of my factors. I've got a to the 3rd, right? That's a to the negative 1st times a to the 4th, and there is a b to the 3rd. So these two equivalents are identical. They will always produce the same outputs, my simplified version and the one that I started with. And then finally, D is the last one here. That numerator, let's clean that up first, right? That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 factors of a. So in my numerator, I have a to the 10th power, and I'm going to cube that, which means it'll be a to the 10th times a to the 10th times a to the 10th, which is a to the 30th. So this is going to become a to the 30th power. In my denominator, I have, there it is, it's a to the 20th power. And yes, 30 factors of a over 20 factors of a simplifies to just a to the 10th power over 1, right? Or I could just say that's just a to the 10th. Right below that, it says what, it says what is the equation of the line that goes through the points 1, 5, and 7, 3. Okay, I can do that, I think. I'm going to begin by finding the slope of this line. I'm not going to be too lazy, but I'll take the 5 and I will subtract a negative 3. So you can see I'm going from my first point to the second, right? It's important to keep this consistent. So 5 minus negative 3, in other words, I've got a numerator of 8. My change in y is 8. Yes, it's the change in y. I took this y and subtracted the other y. 5 minus negative 3 is 8. And in my denominator, my change in x is going to go 1 minus 7. 1 minus 7 is going to be a negative 6. So that means my slope is going to be negative 4/3. This is the slope. Negative 8, or 8 over negative 6 is equivalent to negative 4/3. So down 4/3. So I know my slope, but what I don't know is my y-intercept. So I'm going to calculate the y-intercept. And I've talked about point slope form. You could use that. It would work well here. But I'm going to go ahead and go through the process of finding b. So I'm just going to sub things into y equals mx plus b. And I'll just arbitrarily pick this first point. So I'm going to use the 1, 5. So I'm going to write for y was 5 in that first point. My slope is negative 4/3. And my x value is 1 plus b. So what it looks like I'm doing here is I'm just going to take the number 5 and I'm going to add 4/3 to that, and that will be b. So you can see I just added 4/3 to both sides. 5 expressed as thirds is 15/3 plus 4/3 looks like that's 19/3. So I'm just going to come in here and say, I think I've got it. I'm going to say y is equal to negative 4/3 x plus 19/3. But I remind myself, hey, it is a Friday. It's late. You're tired. Maybe you could be making a mistake. So I'm going to try and think of a way to check that. Let me grab my calculator, and what I'm going to do is if I plug 1 in for x, I should get 5. So let me see here. I can do this a couple ways too. I can do it with a table, but I think I'm going to just do it. I'm going to store x as 1. So I'm going to say 1 store x. So there we go. X is now the number 1. So now I can just type in negative 4/3 and then times x. That looks great. Negative 4/3 x plus 19/3. Oh, I like that. It looks just like it does on my page. Now, when I do that, when I put x as 1, notice this gives me 5. Oh, I see. When I put 1 in, it gave me 5. Now, what about if I put in 7? So it's easy to do this. I'm just going to say 7 store x. Got it. Then I just go grab this expression. Boom. And now that the value of x is 7, it says, oh, look at that. Just like it's supposed to, right? It gave me negative 3. So I'm super happy with this. It's behaving just like it should. So any line that is parallel to this line, right, would have to have a slope of negative 4/3. And any line perpendicular to this would have to have a slope of positive 3/4, right? So we're thinking both here opposite in sign. So it was negative, it became positive, and reciprocal. Fabulous. All right, let's take a look at this next problem. And I apologize that it got kind of scrunched up when I printed this. I did not intend that to happen. Doesn't look great. But couple ways we can handle this, right? One way is just with fraction busters. So if I look at this, this is x plus 1 over x, and that equals x plus 2 over x minus 3. So because I need to be very intentional, I want to try and avoid mistakes like thinking that x plus 1 over x is equal to 1, right? These are terms, right? The x and the 1 are terms. They're not factors. So this is not true. That is not a giant 1, and that's not equal to 1. So I got to be careful with that. Kind of helps slow me down and avoid that if I put parentheses around these things. So I'm going to go ahead and do that. To get rid of the fraction on the right-hand side, I'm going to go ahead and multiply this side by x minus 3. And if it helps, I can think of it, it's x minus 3 over 1. And I'm going to do the same thing on the other side. I'm going to multiply this by x minus 3 over 1. What's nice is now you see I do have something, x plus 2, times something else, right, over, which is x minus 3, over x minus 3. So this legitimately is a 1, right? This is gone. And the only thing left on the right-hand side is x plus 2. Now, over on the left-hand side, I still have a factor of x that lingers in the denominator. So to take care of that, I'm going to go ahead and multiply this by x over 1. And I have to do the same thing on the right-hand side, so I'm going to introduce a factor of x over there as well. As I look at this now, I can see, oh, this is clever. It is multiplication times this thing, multiplication times this thing, multiplication times x. Because it's just a thing times a thing times a thing. This legit is a giant 1, so I can, this x over x may be gone. So if I look at it, right, I can see, what I have to do next, right? I can see it. I have to multiply x minus 3 times x plus 1, and I also have to multiply x times the quantity of x plus 2. So let's go ahead and do that, right? If I multiply this, right, I don't need to do this, but it might be helpful to think about a generic area model. So I can sketch one down here. I'm multiplying a binomial, x minus 3, times another binomial, x plus 1. And when I do that, I get x squared. There's a minus 3x, there's a positive x, and then there's a minus 3. Two of those can be combined, right? The the x and the minus 3x can be combined into negative 2x. So this product ends up being x squared minus 2x minus 3, and that equals, over on the other side, you can see that there's an x that I need to multiply by x plus 2. Simplest form of the distributive property. There's no way I need an area model for that, but just to remind myself, it is an x plus a 2. Here's an x. It's x squared plus 2x. So this equals x squared plus 2x. I can see that both sides have a term that's x squared, so I'm just going to subtract x squared from each side. That leaves me with negative 2x minus 3 equals 2x. Hey, let's add 2x to both sides. Okay, if I add 2x to the left-hand side, it's going to become just negative 3. And if I add 2x over to the right-hand side, it's going to become 4x. And now when I divide both sides by 4, I can see that I think x is negative 3/4. So I'm just going to go ahead and write this in here. X is negative 3/4. And yeah, I want to check it. Why? Because it's Friday and I'm tired. It's nap time. Oh, I did not say that is not a nap time. I'm a big boy. So I'm going to go negative 3/4, store, oops, not there. Negative 3/4, delete you. Enter that, and I'm just going to hit store that as x. There we go. And if I look at the left-hand side of the equation, right, the left-hand side was x plus 1 over 2. So I'm going to grab a fraction. I'm going to look at x plus 1 over x plus 1 over x. And I can see that that gives me negative 1/3. The other side of the equation is also a fraction. It's x plus 2 over x minus 3. And what I want to see is a negative 1/3. And I do. So that tells me that when x is negative 3/4, let me write that neater. X is negative 3/4, right? It makes both sides of this equation equal to negative 1/3. So it is most definitely our solution. One thing I do want to point out before we leave is this is a proportion, right? What's a proportion? It's just a statement when one ratio equals another. So for example, if I have 2/3, that is the same as, let me multiply by 4. It's the same thing as 8/12, right? What did I do to get that? Well, I just multiplied 2 times 4 and 3 times 4. It's a proportion, right? They're proportionate numbers. Anytime I have a proportion, and I want to be real clear, it's one fraction that's equivalent to another fraction, right? This is true. This product, 3 times 8, is equal to 24. And this product, right, this product, 12. Now, why did that not look as dramatic? Oh, because I maxed out the size of it. There we go. And this product, 12 times 2, also equals 24. Right? So whenever you have a proportion, one fraction equal to another, the cross products will be equal. How could that be helpful? Well, if you look, x times x plus 2, and you can see that's exactly what this side of the equation became, right? It became x plus 2 times x. And on the other side, the green diagonal, I've got this x plus 1 times x minus 3, and that's exactly what I ended up with here, right? So Fraction Buster lands at the exact same spot. We ended up getting to where we have a, because it's the proportion, the cross products are equal, or I can just multiply both sides by x minus 3 and then multiply both sides by x to get all the fractions to go away. I know the important thing is that negative 3/4 works because I checked it. All right, let's take a look at this. Hey, perfect for Fraction Busters. Let's use it. So I'm going to go ahead and multiply both sides of this by, I can see I have a factor of 2 and I have a factor of 3. A factor of 6 would be adequate to get rid of all these fractions. I do like to point out that this binomial right here, that whole thing, I'm going to treat it as a chunk. It's 3x minus 2. It's 2 different terms in that numerator. So if I go through and I simplify this, when I multiply the, how would I show this? The 6 times 3x plus 2, that's 6 divided by 2 is 3. This is going to become 9x. And then when I multiply the 6 times 4/3, 6 divided by 3 is still 2. Times 4 is going to become 8. And then I'm going to take and I'm going to multiply the 6 times this thing. Well, 6 divided by the 3 is 2. So what I'm going to have to do is I'm left with a 2. I'm going to have to multiply this 2 times the binomial of 3x minus 2. That's what I'm going to have to do with that. And then the last one I'm going to multiply is this. I'm going to multiply this 6 times the 10, and 6 times 10 is 60. So just a quick bit of simplifying. This is 6 times x minus 4, and this is not equals 60. It's plus 60. Plus 60. So minus 4 plus 60. And on the other side, we've got 9x plus 8. I could take away 6 x's from each side, so that's going to leave me 3x over here plus 8 is going to equal what? Negative 4 and 60 is positive 54. Then I'm going to have 3x, and am I that tired that I'm reaching for a calculator? I'm going 54 minus 8. I did it. Oh no, that doesn't. Did I make a mistake somewhere else? Yeah, I did make a mistake. I've already made a mistake because 60 minus 4 is not 54. 60 minus 4 is 56. Boom. That's embarrassing. So this is actually 56. And then I've got 56, and I'm going to subtract from that the number 8, and that gives me, oh, that's no nice. That's 48. And 48 divided by 3 ends up being a nice result at 16. So we've got x should be 16. Now you've seen how I've fumbled around, right? There's no way I'm going to just leave this as x is 16 and assume I'm right. My assumption is, of course, I'm wrong. So again, this time I'm going to take a 16. I'm going to store that in x. Gotcha. And then I'm going to look at, on the left-hand side, I've got 3x over 2. And I'm going to add to that 4/3 plus 4/3. And that gives me 76/3. Let's see if we get the same thing on the other side. On the other side, I have a numerator with 3x minus 2, 3x minus 2. In my denominator, I have 3. Oh, and then I'm going to add to that 10. And that gives me, that's exactly what I wanted to see, 76/3. So yeah, this answer checks. And you can see right here, it says include a check for your solution. Does your solution make both sides the same? So really, I'm just happy if you wrote something like, hey, 76/3 is the same as 76/3. That's a check, and that's my answer. And the other one I think that made both sides of this, was it negative 1/3? I can go up. I think it was negative 1/3. Yeah. Negative 1/3 is the same as negative 1/3. So this is a check for this one also. All right, moving right along. Is this our last page? It's our last page. We made it to the last page. That's great. All right, so on this problem, this is very similar to the problem that we had that was a geometric sequence earlier, right? So you can think about this way, but I am encouraging you. It says use the system below to help find the parameters, right? What's the parameter? This is the 0th term, and this is my multiplier. So I want to find these parameters to figure out the exponential equation, right, that will hit those 2 points and have an asymptote that's equivalent to the x-axis. Blah, blah, blah. I don't know why I threw that in there. So my strategy has been, and oftentimes is, to go ahead and get a alone in one or both of the equations. So if I look at this equation, if I divide both sides by b cubed, here I am, 156 getting divided by b cubed. And on the other side, I've got a times b cubed getting divided by b cubed. What's glorious is because I've got b cubed over b cubed, and it is multiplication, this is definitely a giant 1, so it can be gone. So I end up with, hey, 156 over b to the 3rd is the same as a. So I have here a wonderful substitution for a. A, right, a, 156 over b cubed, a. That's where I'm going to put that. So let's write that second equation using substitution. So this is going to become 20 equals a 156 over b to the third times b to the 10th. It might help you to see this better, right? B to the 10th is b to the 10th over 1, right? It literally is a fraction. Everything's a fraction. Just a lot of them have denominators of 1. But I've got 10 factors of b in the numerator, 3 factors of b in the denominator. At this point, it's like breathing, right? That simplifies to b to the 7th. So this equation can be rewritten in a simplified form. 20 equals 156 times b to the 7th power. If I divide both sides of that by 156, I get 20 over 156 is b to the 7th. And remember, I'm trying to find my two parameters, a and b. So close to finding b. If only there was a way that I could undo raising something to the 7th power. And I know what you're saying. There is, Mr. Roberts, there is. If you raise both sides of this to the 1/7 power, what? The 1/7 power, you're going to get b to the first. Because over on that right-hand side, when I have b to the 7th to the 1/7, that ends up just becoming b to the first power. So over here I've got b to the first. On the other side, what is that, you say? Well, that's why I've got a calculator. So let me fire that up. There you are. Clear this. I'm going to look at 20. Ooh, I need to figure out what the keyboard shortcut is for the fraction. Wait, clear. Oh, I need to quit all this. Clear this. There we go. 20 over 156, and I'll just press enter. Oh, it reduced. I didn't need to know it did that, but it does. I'm going to raise that to the 1/7 power, and we get something. And I know what you're saying. That looks terrible, and it doesn't look great. But I think that that's b. I'm not willing to bet the farm on it, but I think that's b. I'm going to round it to the nearest, what did it say, hundredths? So I'm going to write this as 0.75. Now, one thing. I'm rounding b to 0.75 here, but I'm never going to lose all those decimals on the calculator. If I need to refer to b again, I'm going to go back to all those digits on the calculator. That's why I love being able to just, scroll up and down on this screen and grab different digits like that. Okay, so we need to figure out what a is. That's our pretty much our last step here. Well, it turns out that a, it's like, hey, look at me. I'll tell you what a is. If you want to know what a is, all you have to do is take 156 and divide it by whatever b is raised to the 3rd power. Oh, I can do exactly that. I could take 156 and I could, I'll go ahead and just hit divided by, here's b, I went up, I got b, press enter, and I'm going to raise that to the 3rd power. I literally have 156 divided by b cubed, and it says, congratulations, a is 376.23 if I'm rounding to the nearest hundreds. So I think I have my answers. I'm going to write down what I think my answers, but I'm definitely going to verify this. So we're going to quickly go y is equal to 376.23. I got to write this smaller. I'm running out of room. Y is equal to 376.23 times 0.75 raised to the x power. Now, to check my answer, right, I'm not going to use those decimal approximations because first of all, I don't want to type them anyways, and I don't need to. They're on my calculator screen. I just need to know where to go get them. So I'm going to go grab that first number. There it is. Doop. There's that. And I'm going to multiply that. So I'm going to hit times. And then now I'm going to go get b. Boop, boop, boop. There's b. And I'm going to raise that b to the 3rd power. And when I do this, it didn't. Oh, I messed it all up. I'm embarrassed. Let me go get it again. There's a times b b to the power of 3. Now, when I do this, I should get 156. And I get exactly 156, right? Because there was enough internal digits that it was that close, huh? So, hey, good news. Good news. My answer has passed my first check, right? I verified some truth here because it did what it's supposed to with that point. Let's try the other point. So again, I'm just going to go get the 376. I went up. So I'm just going up and down. I go up and I got that number, enter. I'm going to multiply that by b to the 10th this time. So let's go get b. There it is. And I'm going to raise that b to the 10th power. And when I do that, I get, okay, beautiful. Look at that, 19.99999. Come on. It's 20, right? Clearly, we're having to round off here. There's a lot of digits going on for this problem. But this is a problem I can be smiley about. Nap time. Last problem, and you know, I don't think a lot of us thought of these like this, but if you want to, you can arbitrarily say, look, I'm going this direction because I want to find this one. I can say, oh, I'm going this direction because I want to find this, and I'm going this direction because I want to find this. So remember, way back at the beginning of chapter 8, we said that the scale factor is the new dimension divided by the original. So I can take 8 over 12. That's the scale factor for these similar quadrilaterals. So if I take any dimension, like for example, if I take the 12 and I multiply that by this scale factor of 8/12, it's going to give me the new one. Oh, that's terrible. New over, what am I doing? If I take 12 and I multiply that by, oh, of course that has to be 8, by 8/12, it better give me, and it does, yeah. So if I take, because I'm going this direction, if I take any of these dimensions and I multiply by the scale factor, it's going to give me the corresponding side, right? So, hey, I know that I need to start at 9, and I'm just going to multiply that by my scale factor of 8/12. By the way, that does reduce to 2, divide by 4, 2/3. Yeah, that's great. In fact, 9 times 2/3. Yeah, I needed to see that. So I get that this one's 6. That's great. So A was 6. Let's look at B. Okay, scale factor again. I think I got this. It's going to be the new dimension, 12 divided by the old. 12, that's not 12. 12 over 6 looks like the scale factor is 2. And you can see that. I could see that. I didn't need to do that. It's 2. So 4 times 2 gives me 8. So this has to be 8. Looks like this one's answer is D. The last one we have here is scale factor. Again, why am I doing this? It's tired. I'm trying to prevent mistakes. It's my tired time. Let's see. New dimension 4 divided by old 4 over 16. Looks like my scale factor is 1/4. If I take 24 and I multiply 24 times 1/4, oh yeah, I'm going to get 6. 6. This last one was C. Well, that's it. That's a complete walkthrough of the entire test. And I think it's time now for a snack and maybe a soft pillow and a nap. Thanks for coming, joining, and I hope to see you again soon.